Section: Introduction. In this section, we discuss the rapid rise of artificial intelligence tools that have become crucial for enhancing productivity and automating tasks in various fields. Large language models, like ChatGPT, have significantly sped up processes, allowing users to accomplish tasks in minutes that previously took much longer. Since ChatGPT's launch, AI capabilities have improved greatly, and the emergence of powerful open-source models has made these technologies more accessible. Researchers can now fine-tune and continue training these models, often achieving performance that rivals or surpasses proprietary models on specific tasks. However, the use of these advanced language models in standard cybersecurity practices is still limited. Cybersecurity professionals encounter several challenges, such as strict safety measures from commercial providers, a shortage of clean and publicly available cybersecurity datasets, issues with model inaccuracies, and difficulties arising from changes in data distribution. Meanwhile, malicious actors have the resources to create custom, closed-source models for harmful purposes. The diverse nature of cybersecurity, which ranges from phishing detection to cryptographic analysis, complicates the development of a universal security AI, leading to a landscape filled with fragmented, task-specific tools. In our work, we present Foundation Sec-8b, a language model tailored for cybersecurity, built on Llama 3.1 to 8b. Our model demonstrates significant improvements over Llama 3.1 to 8b in cybersecurity benchmarks. We also provide trained checkpoints for the research community, along with thorough evaluations that showcase the model's capabilities. This contribution aims to further research on applying language models to cybersecurity tasks and to support defensive cybersecurity practitioners. We also explore the concept of continued pre-training, which enhances domain-specific adaptation for transformer-based models. This method has been shown to improve performance in various fields, including medicine, law, mathematics, and coding. We reviewed several benchmarks and evaluation methods at the intersection of language models and cybersecurity, focusing on assessing the knowledge of pre-trained models rather than their behavioral robustness. We selected 3 cybersecurity benchmarks framed as multi-class classification tasks, as pre-trained models often struggle with open-ended questions. Our focus is on multiple-choice question answering and root cause mapping tasks. In the multiple-choice format, each question has 4 options with 1 correct answer, while the root cause mapping task links vulnerability descriptions to specific identifiers. CTI Bench, which focuses on cyber threat intelligence, includes practical tasks but requires advanced instruction following capabilities. We adapted 2 tasks for evaluation: multiple choice questions and root cause mapping. The multiple-choice section consists of 2,500 questions from various cybersecurity frameworks and regulations. The root cause mapping task assesses a model's ability to connect vulnerability records to their corresponding entries. The cybermetric dataset was created from various cybersecurity documents and transformed into a multiple-choice format with the help of GPT 3.5. Human experts validated the questions and answers to ensure their accuracy and relevance. We utilized the 500 sample version of Cybermetric, as larger sets contained only AI-generated questions without human validation. SecBench includes both multiple-choice and short-answer questions, evaluating knowledge retention and logical reasoning. A significant portion of its content was developed by human experts, making it more challenging than other benchmarks. Released in December 2024, SecBench features both English and Chinese sections, but we focused on the English portion, which contains 600 samples. Section Summary. In this section, we discuss the rapid advancement of AI tools, particularly large language models, LLMs, like ChatGPT, which have transformed productivity across various fields, including cybersecurity. We introduce Foundation Sec-8b, a specialized LLM that outperforms existing models on cybersecurity benchmarks, and outline our evaluation methods and datasets, emphasizing the need for effective domain-specific adaptations in cybersecurity practices. Section: MMLU. In this section, We evaluate whether continuing to pre-train our model on cybersecurity data impacts its general knowledge by using the Full Measuring Massive Multitask Language Understanding (MMLU) benchmark. MMLU encompasses a wide range of subjects, including science, humanities, and social sciences, which helps us assess the model's retained knowledge across various fields. This evaluation allows us to identify any potential overfitting or catastrophic forgetting, ensuring that our focus on cybersecurity does not significantly harm the model's general reasoning and factual recall. We acknowledge that several studies have explored the use of large language models, LLMs, in cybersecurity. While much of the research has concentrated on code generation, our model is not specifically designed for coding tasks. Our main objective is to embed essential cybersecurity knowledge into a pre-trained language model, providing a solid foundation for various applications beyond just code generation. We include several notable models trained on general cybersecurity data as baselines in our evaluations, except for the last model we discuss. White Rabbit Neo v2 was one of the first open-source cybersecurity LLMs based on the Llama 3.1 family, available in 8B and 70B versions, and aimed at offensive security tasks. Primus created a cybersecurity dataset from sources like MITRE and Wikipedia, containing nearly 2 billion tokens, which was used to pre-train models based on Llama 3.1 to 8B. Security LLM, although not detailed in a technical report, is an open-source model based on Hugging Face's Zephyr series and built on Mistral 7B, designed as a security assistant and fine-tuned across 30 domains, including cloud security and compliance frameworks. SecGemini is a unique LLM specifically designed for cybersecurity, enhanced with reasoning capabilities and live threat intelligence access, but it is currently in closed preview and not publicly available. A major challenge in developing LLMs for cybersecurity is the need for large amounts of high-quality data to achieve meaningful improvements. While other domains often use tens or hundreds of billions of tokens for effective domain-specific knowledge infusion, current cybersecurity models typically rely on fewer than 2 billion tokens. Given that cybersecurity is a niche area, we adopted a two-pronged approach for data collection. First, we used general-purpose scrapers with a relevancy filter for broad coverage. Second, we created custom scrapers targeting high-quality cybersecurity sources that are not easily accessible through standard methods. We opted to build our dataset from scratch instead of filtering existing large datasets, as security-related content often appears non-English, due to code and abbreviations, leading to high perplexity. Existing datasets like FineWeb do not align well with cybersecurity needs, as their quality filters may exclude valuable content such as CVE descriptions. To enhance our cybersecurity data collection, we implemented a wide-net internet crawler. This crawler starts with a set of initial URLs, retrieves and stores the raw content, and then extracts new links for further processing. We seeded the crawler with URLs from various cybersecurity domains and prioritized exploration within a domain before moving to new ones. This hybrid strategy combined breadth-first and depth-first search methods. To maintain focus, we applied a relevancy filter to prune irrelevant content, ensuring that only pages meeting our criteria were included. Section Summary. In this section, we evaluate the impact of continued pre-training on cybersecurity data using the MMLU benchmark to ensure our model retains general knowledge while specializing in cybersecurity. We also describe our data collection approach, which includes deploying a wide net scraper to gather high-quality cybersecurity content, addressing the challenges of limited existing datasets in this niche field. Section: Data Preprocessing. In this section, we describe our data preprocessing efforts. We collected over 4 terabytes of raw data and created a scalable pipeline to filter, clean, and transform this data into a high-quality dataset for pre-training. By using existing tools, we built composable data pipelines that ran on a cluster of virtual machines. After processing, we reduced the original data to just under 25 gigabytes of clean text, which is about 0.6% of the original size. This low yield is due to extracting only text from noisy HTML and removing low-quality files, with around 90% of the files being filtered out. Text extraction was the most demanding and time-consuming part of our pipeline. We converted various file formats into clean Markdown files and tested several tools to find the best one for each file type based on its format and size. To ensure our dataset focused solely on cybersecurity documents, we implemented a relevance filtering pipeline. Initially, we used a keyword matching method with a list of about 800 cybersecurity terms. While this was efficient, it had a high false positive rate. To improve this, we developed a small transformer-based classifier using a labeled dataset of 26,000 documents, balanced with 13,000 relevant and 13,000 irrelevant samples. Our classifier significantly outperformed the keyword filter, achieving an F1 score of 0.924. We also added extra filters to remove low-quality data, including a language filter and regex-based heuristics. We conducted experiments to evaluate how well these filters retained high-quality, relevant documents. We randomly sampled 1,000 documents from our raw dataset and assessed them for quality and relevance using a language model. A document was included only if it met both criteria. Some important sources, like the CVE and MITRE ATT and CK databases, were excluded by these filters, leading us to discard most heuristic-based filters from our final pipeline. Before training, we took additional steps to clean and format the data. We used an n-gram Bloom filter to remove duplicates at the paragraph level and followed best practices to filter out personally identifiable information. We also upsampled high-quality data related to tactics, techniques, and procedures. Finally, we split the resulting 5.1 billion tokens into a 99% training set and a 1% test set. We trained a Llama 3.1 to 8B model on the curated dataset using a pre-training approach, packing documents into sequences of 4,096 tokens for efficiency. Training was conducted with deep speed on a multi-node compute cluster, using the AtomW optimizer with a cosine decay learning rate schedule. We considered benchmarks from our experiments and discussed other cybersecurity benchmarks in the literature that we chose not to include due to misalignment with our objectives. The models we reviewed serve as baselines for comparison, and further details can be found in their model cards on Hugging Face. To ensure fair evaluation, we carefully designed our prompting strategy, as poor formatting can obscure a model's capabilities. Since log probabilities are not available for closed models, we evaluated based on predicted tokens. Pre-trained models were assessed using 5-shot prompts, while instruct fine-tuned models were evaluated in a 0-shot setting to avoid inconsistencies. We prompted them with just the question and extracted answers using regular expressions. Additional implementation details are provided in the appendices. Section Summary. In this section, we describe our scalable preprocessing pipeline that transformed over 4 TB of raw data into a high-quality dataset of under 25 GB, focusing on text extraction, relevancy filtering, and quality assessment to ensure the final dataset was relevant to cybersecurity. We implemented various filters, including a transformer-based classifier, to enhance data quality and relevance, ultimately preparing a curated dataset for training our Llama 3.1 to 8B model. Section: Results. In this section, we present our results from evaluations conducted over 10 trials to address randomness in token sampling and the selection of few-shot examples, with a temperature setting of 0.3. We report the average accuracy along with the standard deviation from these trials. Our findings are summarized in a table, and we also assess the models at a temperature of 0, with those results shown in another table. For the security benchmark performance, we find that Foundation Sec-8B achieves top performance in its size category on the chosen CTI tasks, matching GPT-4o Mini closely. It is just 0.8 points behind GPT-4o Mini on the CTI Bench MCQA task but exceeds it by 6.1 points on CTI Bench RCM. Additionally, Foundation Sec-8B outperforms both Llama 3.1-70B and White Rabbit Neo V2-70B by about 1 point on CTI Bench RCM, while it is less than 2 points behind on CTI Bench MCQA. Notably, it shows an improvement of over 3 points in accuracy compared to its parent model, Llama 3.1-8B base. We highlight that these gains are significant for a general-purpose model applied to a specialized area, which aligns with trends seen in previous studies. Overall, our results establish Foundation Sec-8B as the leading model with 8 billion parameters for CTI security tasks. In terms of general benchmark performance, we follow established practices by evaluating our model on the full MMLU benchmark to ensure that our training does not lead to significant performance loss. Foundation Sec-8B scores 0.593 with a small margin of error, compared to 0.617 for Llama 3.1-8B, indicating a consistent drop of 2.4 points as noted in earlier research. Regarding use cases, we recognize that large language models in cybersecurity are becoming practical tools integrated into important operational workflows. Foundation Sec was designed with these applications in mind, and we identify 3 main areas where it is currently being tested or used, either in its pre-trained state or after fine-tuning. For society acceleration, we note that security operations centers deal with numerous alerts that need triage and contextualization. Foundation Sec is being tested to automate parts of this process. When fine-tuned or prompted correctly, it can summarize alerts into clear case notes, create incident timelines, and draft reports to assist in incident resolution. These functions help reduce the time needed for triage and allow analysts to manage more alerts with greater accuracy. In proactive threat defense, Foundation Sec is being utilized to model and simulate attacker behavior. This includes extracting tactics and techniques from threat intelligence, prioritizing vulnerabilities based on their impact, generating hypotheses about attack paths, and drafting penetration test reports. We have found that fine-tuning Foundation Sec for extracting MITRE ATT and CK techniques from unstructured reports significantly improves performance, outperforming a similarly sized model by over 10% in this task. Lastly, for engineering enablement, we see that security engineering teams often struggle to enforce security standards in fast-changing development environments. Foundation Sec is being used to improve these workflows by offering development guidance, validating configurations, and aiding compliance efforts. When applied effectively, it helps teams interpret security policies, validate configurations against best practices, assess compliance evidence, and analyze security policies for inconsistencies. These tasks require a blend of contextual awareness and specialized knowledge, which Foundation Sec is well equipped to provide. If anyone is interested in utilizing Foundation Sec for cybersecurity applications or research, we encourage them to contact Paul Kasianik or Dhruv Kedia at Foundation AI.